Okay, so these are the solutions for section 4.3, the larger or longer questions that I left out of the lesson. So we'll start here. Two trunks sit side by side on the floor. We have a large trunk and a small trunk. I've already drawn a free body diagram. I've left off the vertical direction for now. I should probably do this, so just separating the system from the parts. Okay, so the first question is determine the magnitude of the maximum force the person can exert without moving either trunk. So if you look down here, I've made a few calculations just to begin with. I said as a system the combined mass is 86 kilograms. That means my Fg, so multiplying the 86 by 9.8, I get a Fg of 8.43, which means my normal force is the same because these aren't moving in the vertical direction. If I apply the coefficient of friction, which was given, I get a force of friction of 295 newtons. Now, we might be a little bit off from rounding myself in the textbook, but until I overcome that 295 newtons, that's the largest force you can apply before these things move. So I think the book has, 290 newtons, so they round it a little bit differently. So until you overcome that 290 newtons, these don't move. So the maximum force you can exert will be 295 newtons if we use my numbers. Okay, going on to B, calculate the force the larger trunk exerts on the smaller trunk. Now, we're going to take Fa as being the 295 newtons. Okay, because that's as large as you can push on this without it moving. So if we write an F net statement here, okay, I'm just going to give myself a little bit more room. If I write an F net statement based on this free body diagram here of the first box, I would have Fa minus the force of friction minus this Fc, which is a contact force between the two boxes. Okay, so now it's not moving, so A is 0, so F net's going to be 0. That's a really important piece that's not explicitly stated, so you have to make that connection. Better make a better equal sign than that. Okay, so now Fa is 295 newtons. The force of friction is going to be mu times Fg of the large box. Okay, and then we have minus the contact force. So 0 equals 295 minus 0.35 times 52 times 9.8 minus that contact force. Okay, we could do a little rearranging and say the contact force is going to be 295 minus 0.35 times 52 times 9.8, and we should get 116.6 newtons. Now we'll probably be a little bit off from the textbook only because our numbers are slightly different from rounding. So calculate the force, we would find it's 120. We got 116.6. If we round it off, that's about right. Okay, now part C, would either answer change if the person pushed in the opposite direction on the smaller trunk? Well, the first one would not, because we evaluated at a system. So if you pushed on the smaller box towards the left, because you'd evaluate as a system, it would take the same amount of force to get the system moving. Now, it does get a little bit different though when you push on the smaller box to the left in terms of their contact force. So if we take all of this, I'm just going to try and grab all of this and just slide it a little bit over. Okay, and now if we look at the contact force of the small box here, I'm going to write an F net statement, and I'm going to say positive is to the left. So again, we're going to go F net equals Fa minus Ff minus Fc, contact force. And you'll notice that's the exact same first line. F net is still 0. Fa is still 295. Now here's where it gets a little bit different. Now the force of friction changes because I'm now working on the small box. So I'm going to have 0.35 times 34 times 9.8 minus Fc. Okay, so now if I bring Fc over to the other side, and we do that quick calculation, 295 minus 0.35 times 34 times 9.8, we get 178 newtons. Okay, so by pushing on the smaller box, the contact force between them is greater, okay, because less of the applied force is being used up, if you want to think of it that way, by the friction force. Okay, so because there's a smaller friction on the smaller box, it uses up less of that applied force, so more force gets transferred to the second box. Cool, and the textbook got an answer, I think of, oh, I'm one ahead. A slightly different number. So now number 2, I already revealed the answer, whoops. Number 2 looks like a complicated problem, but it's not as bad as it looks. Okay, the key to remember here that the Fg in this pulling down here, the Fg on the mass is going to translate into a tension force that will be exactly the same because the system isn't moving. The key to remember is that a pulley just changes the direction. Okay, so this tension force comes up and around, and then Newton's third law, equal and opposite actions and reactions. The force that's applied to the box looks like this. So this has some sort of tension force of 17.6 newtons pulling to the right. Okay, so now if this box is not moving, okay, that means there must be some sort of friction force that's balancing that force of tension. So now we have FF, we have FN, 39.2. So if we put those two pieces together, we can find the mu of 17.6 over 39.2, and 17.6 divided by 39.2 is 0.45, and we can see, hey, that's the same answer they got. Okay, so there's one set out of the way. Next set, now I've typed out most of this just to make it a bit speedier. We have a hockey puck. It's initially traveling at 21.2 meters per second to the west, so I have my positive direction to the left, or the west. It's the direction the object's moving. The coefficient of kinetic friction for the puck and the ice is 0.005, so that's very small, so not a lot of friction force acting in this situation, which we would expect from a hockey puck on ice. What is the speed of the puck after traveling 58.5 meters? Okay, so I drew my free body diagram. So I have my normal force and my gravitational force. The puck is not coming off the ice, so those are going to be in equilibrium. The puck is moving to the left or to the west, which means my friction force is going in the opposite direction and opposing. I do a quick calculation using my friction force and coefficient equation. Okay, so I plug in 0.005, 1.7 newtons, and I come up with a friction force of 0.0085. So that's a really small force, which we expected because we're on ice. Okay, I go to my F net statement just for horizontal direction, and the only force acting on this object is the force of friction, and again it's in the opposite direction, so it gets a negative value. Okay, I plug that in. The mass of the hockey puck is 0.170 kilograms. By the time I divide that out, I come up with an acceleration that's negative and 0.05 meters per second squared. The negative makes sense because it's opposing the motion. It should, in theory, slow this hockey puck down. So let's see the rest. Now the rest becomes a bit of a kinematics equation. Okay, and we'll get used to that. We're going to merge a lot of this stuff together. So I have listed out my kinematic pieces of information. I have an initial velocity of 21.2. I have my negative acceleration. I'm traveling 58.5 meters, and I'm trying to find the VF. So if I plug those numbers in, and then by the time I calculate the right-hand side of this expression and then square root it, I didn't type that in, but make sure you square root that. You end up with 21.06 or 21.1 meters per second. So you've had very little change in your velocity, and that's because you have a very small acceleration. Okay, in the opposite direction, and whoops, I went too far again. So that's part here, 21.1 meters per second. After being played on for a while, the ice becomes rougher. So I'm not going to do this whole question again. What you do though is you take this coefficient of friction right here and you replace it with 0.047 and trace it through the problem. And you should come up with 6.24 meters. Okay, and you can sort of work that problem backwards. And then lastly here, an electric motor is used to pull a 125 kilogram box across a floor using a long cable. The tension in the cable is 350 newtons and the box accelerates at 1.2 meters per second squared forward for 5 seconds. So immediately a couple of things should be jumping out at you. There is an acceleration given, a time given. Okay, they're probably going to have to bring some kinematics into this problem, and let's go at it. So the cable breaks and the box slows down. That's the other piece. This is a two-part problem. So there's one part where there's an applied force, and then there's another part where there's no applied force. So this is a two-part problem. Calculate the coefficient of kinetic friction. So if I get my equation out here, I say, well, I know my Fn, but I don't know my coefficient and I don't know my force of friction. So I have two unknowns in one equation. I can't possibly solve this, so I have to do some more work. Okay, so I've already set up my free body diagram. I've already determined that Fg and Fn are 1,225 newtons. I have my applied force of 350 newtons. So I'm going to go straight to my Fnet statement in the horizontal direction. Okay, so I'm going to say I have 350 minus the force of friction. And again, I'm trusting the system. This is why I wanted to show this example. I'm trusting what I've shown you and that this method will work for lots of different styles of problems, because you'll be looking for the information going, I don't have that. Well, here's a way to find some of the missing information. So Fnet equals 350 minus the force of friction. Fnet is the same as mass times acceleration. Okay, and oddly enough, hey, I actually have mass and acceleration. So I can put in 125 for the mass, 1.2 for the acceleration, 350 is the applied force, and look at that, lo and behold, I can actually solve for the force of friction, which is important because if I can solve for the force of friction, I have the normal force. I can calculate that missing mu, which is what part A was asking for. So if we rearrange this and we get a force of friction equals 350 minus 125 times 1.2, and we get 200 newtons. Okay, and now that I have that force of friction, I can take the normal force and find my mu value. So I have 200 divided by 1,225. So I get a coefficient of kinetic friction of 0.16. Okay, and if we slide up here and check the textbook answer with us, if I can find the eraser tool, there it is, 0.16. So how far does the box travel up to the moment the cable breaks? Okay, so we get a couple pieces from this. We have I pull 100 bar. Does it give us tension of cable and the box accelerates? Cable breaks and the box slows down and stops. How far does the box travel up the moment the cable breaks? So now we have to look at this problem again. It's kinematics. Okay, so we're going to have to do some sort of acceleration. We're going to assume that the initial velocity was 0, and we'll go from there. So let's get another color here to start with. So we're going to say VI equals 0, acceleration equals 1.2 meters per second squared. The time value was 5 seconds. And now we're trying to find D. So D equals VIT plus 1/2 AT squared. So D equals 0 plus 1/2 1.25 squared, and we should get D equals 25 times 1.2 divided by 2 equals 15 meters. Okay, so the box should travel in that first 5 seconds about 15 meters. Let's just check in. There's the 15 meters. Okay, now here's where it changes. How far does the box travel from the moment the cable breaks until it stops? Now this is really important because there's no longer an applied force, which means our Fnet statement has changed. So our Fnet now becomes negative force of friction. Okay, our coefficient of friction we got in part A is right here, so we're going to have to use that. So the mass times acceleration is going to equal mu times the normal force, and this is negative, so the mass is 125. We know this is negative, this is 0.16, this is 125, and this is 9.8. Okay, to get me my normal force. Okay, I guess I could put in the 1,225. Didn't even read my own writing. Silly me. Okay, so if we take our 0.16 times it by 125 times it by 9.8, divide by 125, those would have canceled. I end up with let's say 1.6 meters per second squared, and that's negative. Okay, so now I'm going to combine some of the parts I found in B. Okay, so now I have an acceleration. I'm back to doing another kinematic problem. Let's change to a different color. Kind of wandered into my own space here. So I have an acceleration. I have a final value of 0. I'm trying to figure out how far it travels. How far, right here, how far. So I need a d value is what I'm looking for. And it would be really handy if I knew the initial velocity. Well, that might be where I can jump back to the question on this side and say, well, I knew the acceleration and I knew the time and I knew it started at 0. So if I had to, I could have just found VF over here. So 0 plus 1.2 times 5. So that should be 6 meters per second, and that final value of the first part of the problem becomes the initial value of the second part of the problem. Okay, so now if we go back to that side, we have an acceleration, a velocity for final, velocity initial, we're looking for a d, so I'm going to use this equation. I know this is 0. I know this is 6 squared. I know this is 2. This is negative 1.6. And this is d. Okay, so by the time I solve, I'm going to have negative 36. Better give myself a little more space. Minus 3.2, or sorry, negative 3.2d. Divide that out. And 11.25 meters is the distance the box continues to slide until it comes to a complete stop. And that's the second part of the problem. And if you put the whole thing together, you could say the total distance traveled would be this 15 plus this 11.5, and the total distance would be your 26.25 meters. Okay, so let's just pop up here and double check our numbers. And 11 meters, we had 11.25. I'll consider that a victory. Thanks for watching.